So in this problem, we have a mass of 60 kilograms that's applied at point D, and we're asked to determine what is the tension in cables BA and BC in order to support the 60 kilogram cylinder. So in this type of problem, the first thing that you would do is you're going to draw your free body diagram at the point of interest. So in this case, it is going to be at point B. All right. So at point B, we're going to draw. First, we're going to draw the shape of our particle, which is just a dot. Then we're going to draw all the known forces, known and unknown forces on our particle. So we have our weight of our particle, all right, our weight of our mass. So we know that that's going to be equal to mg. All right. We know we also have the tension in the cable from point B to point C. And we have the tension in the cable from point B to point A. All right. We are also going to include, we're going to draw our horizontal axis here. We know that TBC is at a 45-degree angle from the positive x-axis, and we're given that TBA acts along a 3, 4, 5 triangle. Okay, so the last thing we'll define here is that we're just going to use a standard XY coordinate system, and then that is our completed free body diagram on the system. I guess we could also solve for the total weight by multiplying by 9.81, the mass by 9.81 meters per second squared. If we do that, we end up getting 588 588.4 units. All right. So the second part of the equation, or the problem, is we're going to set our resultant force, which is just the sum of all of our forces, equal to 0, and solve for our unknowns. Okay. So in this case, our unknowns are TBA and TBC. So the sum of all of our forces is equal to TBA plus TBC plus our weight. All right, so we're going to define each as a Cartesian vector. So we'll start with TBA. So it'll have an x component and a y component. All right. So TBA is going to have an x component that's going to be equal to minus 4/5. So we're using the adjacent side of our triangle and the hypotenuse of the triangle to get that ratio times the magnitude of our force TBA, and then the y component is going to be equal to 3/5 times TBA. All right. So that's the opposite side of our triangle and the hypotenuse of our triangle. All right. And then the TBC is going to be equal to the magnitude of TBC times the cosine of 45 degrees times I plus the TBC times the sine of 45 degrees, J. All right, we can simplify those down to radical 2 over 2 TBC times the unit vector I plus radical 2 over 2 TBC times J. Right. Then the last thing here is what do we got? TBA, TBC, and then the last force we have is our weight. So our weight is only going along the negative z-axis, so that's going to be equal to 0 newtons along the positive x-axis, and then for the y-axis we're going to get minus 588.4 newtons times J. All right, so if we sum these all together, we can get our resultant force. Alright, so our resultant force is going to be equal to minus 4/5 TBA plus radical 2 over 2 TBC times I plus, 3/5 TBA plus radical 2 over, plus radical 2 over 2 times TBC minus 588.4 newtons J. Alright, so we can set both of these equal to 0. So if we do the forces in the x, and we set that equal to 0, so that's the left term here, what we'll end up getting is we'll get 4/5 TBA is equal to radical 2 over 2 TBC. So we can solve for TBA in terms of TBC. So we'll get TBA is going to be equal to 5/8 times radical 2 TBC. Okay, we can use this equation and we're going to plug it into the sum. All of our forces in the y direction are equal to 0, which is this component on the right hand side of our resultant force. So if we do that, we'll end up getting so we get 3/5 times TBA, which is equal to 5 divided by 8 radical 2 TBC plus radical 2 over 2 TBC minus 588.4 newtons, which is going to be equal to 0. So if we rearrange this all, what we end up getting is we get TBC, or so I should say we get radical 2 over 2 times 3 over 4 plus 1 times TBC is equal to 588.4 newtons. If we divide our coefficient on the left-hand side of the equation on both sides, what we end up getting is we'll get TBC is equal to 475.499 newtons, and we get TBA is equal to 420.285 newtons. All right, so once we solve for TBC, we could then plug it in to this equation here, and we can solve for TBA. So if you round those both the three significant figures, we get 475 newtons for TBC, and we get 420 newtons for TBA. All right. So just to summarize what we did in this problem, we looked at the problem statement, and we were able to identify a point where we had all of our forces intersecting. So the point was point B. All right, once we had that, we drew the free body diagram at that point. So we included all the forces that were being applied at that point. We added a coordinate system, and we included all the important angles and other geometry that we needed to then apply our equilibrium equation. So for our equilibrium equation, we just summed up all the forces applied at that point, at point B, and we set them equal to 0. So we define each as a Cartesian vector. We found our resultant force, and then we set both the x and the y components equal to 0 and solved for our two unknowns using those two equations. Okay, and we were able to then solve for the magnitudes of those forces. Okay. All right, so that concludes this problem on 2D equilibrium of a particle.